Video covers limits and continuities. In particular, the video goes through the intermediate value theorem for continuous functions and uses of the functions for checking whether a function has a root and the location of that root. Intermediate value theorem for continuous functions. To start with, we're going to go ahead and take a look at this x, y axis and the function that's involved. The function is called y equal to f of x, and this is exactly what the function is. Now we pick 2 points A and B, which are endpoints for the graph. We will take the interval from A to B as a closed interval, and obviously the function is continuous in this closed interval. The function also, for A there is a value for y which is represented by f of A. For B there is a value for B and it's represented by f of B, also on the y-axis. And if there is any constant value for y, so this is an extra value for y that lies between f of A and f of B. For this value, if we draw a line to the function and then take that line down, we will figure out a point C between A and B, and that point C, f of C, is going to be equal to y naught. And this is basically what the theorem, intermediate value theorem for continuous function, is all about. It states that if we have a closed interval A and B and the function is continuous at the closed interval, and between f of A and f of B there is a constant y naught, then there is a value C between A and B such that f of C equal to y naught. That's basically what the general formula or the general statement for the function. We can just summarize that as, if a function f of x is continuous on a closed interval A comma B, and if f of B greater than f of C greater than f of A, then the relationship B greater than C greater than A holds, which indeed is the case. Another corollary is, if f of x is a continuous function on an interval, and that's closed interval A comma B, and f of A and f of B have opposite signs, then C is the root of the function f of x, and C lies between A and B on the x-axis. These are some of the important points that we want to keep in mind. Number one, if f of x is a continuous function in the closed interval A comma B, and f of A and f of B have opposite signs, then f of x has root C between A and B on the x-axis. Number two, if f of x is an odd function or a one-to-one function, then it must cross the x-axis at a single point. Number three, assume at x equals to m on the x-axis, the closed interval A comma B is divided into two halves. If m is not the root, then the search for the root should take place in the interval A comma B, which is the left half, if and only if f of A and f of m have opposite signs. Otherwise, the search must take place in the interval m comma B, which is the right half. Number three, the search for a root of a function uses midpoints of intervals to locate the root, and it will locate the root. Finally, the following example illustrates how the root of a function can be searched. We're now ready to see how we can locate the root of a function. So locating the root of a function, before we do that, let's go ahead and take a look at this note. The note states that search for a root between 2 points on the x-axis only when their y-axis corresponding values have opposite signs. We will keep this one in mind. We have the xy plane and we have the function f of x. Its endpoints are f of b and f of a right there, and this function is piecewise and it's continuous because the function must be continuous on the closed interval a and b, and assume that the function is continuous. Obviously, since the function is crossing the x-axis, then the point that the function crosses the x-axis is a solution for the function. For example, if this point we call it c, then f of c must be equal to 0. Now let's just assume that we don't know where the root is and we want to search the root between a and b. So let's get rid of c. So c disappeared. Now it's a strategy. Our strategy is to make sure that we search only when the endpoints have opposing signs. That means the sign of f of a now is negative, sign f of b is positive, so both have opposite signs, and now we are qualified to go ahead and search between a and b for the root. To do so, the first thing is we have to divide the interval into equal halves, and we're going to go ahead and search for the root. To do so, let's call this point mid, and then once we have this point mid, let's go ahead and do the search from the left side or the left half. So we'll search this half, but we cannot search this half unless these endpoints, their corresponding y values must have opposite signs. So let's see the sign of mid. If we compute mid based on the function, it's going to have, it is y value negative. So since the y value of mid is negative and the y value of a is negative, we cannot search between a and mid as we just mentioned on this note. So that means we have to stop the search on this side and move the search to the right side between mid and b. So let's go ahead and bisect this one into two equal halves. So let's call this one M1. Now we can also go ahead and do the search, but before we do that, we have to figure out what is f of M1, and f of M1 is negative. Since f of M1 is negative, we know that we cannot pair it with any negative value on the left, because we don't want to go to the left, because we know that we cannot find the root right there. So our only direction is to the right. So if we have f of M1, then we will pair it with f of b because they have opposing signs. And if we do so, then we're going to go ahead and go to the middle between M1 and b. The middle will give us M2. Now that we have M2, we have to look at f of M2, but we can see that M2 is right where the root is, so f of M2 will definitely be equal to 0, and f M2 is really where the root is. That's it for this demonstration. Let's move on to see what is next. Next, let's show that the function f of x equal to x minus 1 cube has a single root in the interval between -2 and 2, the closed interval. First, let us provide a table for the function. This is x, this is f of x. These are selected values for x, and these are the corresponding values for the function evaluated at x. Now we can also plot the function, and from the plot we can see that the function is one-to-one function, and since we're given the interval between -2 and 2 to search for the root, this interval, we're going to go ahead and zoom into the interval and proceed. So suppose that the root is in the middle between -2 and 2. Now here is -2 and this is +2. The middle is 0. So let's see if the root is at the point x equal to 0. The middle point between -2 and 2 is x equal to 0, but f of 0 equal to -1. If we go over here, f of 0, this is 0, f of 0 is equal to -1. Therefore, x equal to 0 is not the root, since f of 0 is not equal to 0. Next, what we have to do is we have to look at the left-hand side and also look at the middle point on the left-hand side. The middle point on the left-hand side is -1. So let us check and see -1. The middle of the left-hand side is between -2 and 0, and that's at x equal to -1. But f of -1 equal to -8. F of -1 equal to -8. So we can also conclude that x equal to -1 is not the root. Now we went to the left and we checked the middle of the left half. It's not the root. Let us go ahead to the right half and check the middle of the right half. This is pretty much a repetition where we have the right half between 0 and 2 and its middle is 1. So let's go ahead and check f of 1. So f of 1 equal to 0. From here we can see f of 1 equal to 0. That means what? That means x equal to 1 is indeed the root, which is also known as the solution for the function f of x equal to x minus 1 cubed. Let's take a look at another example. Show that the function f of x equal to x minus 1 has a single root in the interval between -2 and 2. This is a closed interval between -2 and 2. To start with, let's build a table for this function, and this is the table, the x values and the function's values on the right. Now we can just show the graph of the function. It is a straight line because this is the linear function, and it crosses the y-axis at -1 and it crosses the x-axis at 1. So obviously the solution is x equal to 1, the solution for this function, and obvious, it's right there, solution equal to 1, because you can say x minus 1 equal to 0 and that will give you x equal to 1. So let's go ahead and see if we search the same way between -2 and 2, if we can find the solution. So to start with, suppose that the root is in the middle between -2 and 2. So here is an enlarged. We focus, we zoom in. So we have -2 and 2 there, and this is 0 in between, and we're looking to see if the root is in the middle. That means if the root is at x equals 0. Now if we look at x equals 0, we will find that f of 0 is not equal to 0, because over here f of 0 equal to -1. So f of 0 equal to -1 proves that x equals 0 is not the root, since f of the root must be equal to 0. Now we have to go ahead and go to the left side, the left half, and try to see the middle point in the left half, whether or not this point is the root. We will do the same test. So the middle point between -2 and 0 is x equal to -1. But f of -1 is equal to -2. Here is x equal to -1. This is f of -1, which is equal to -2. Again, f of -1 implies that x equal to -1 is not the root, because one more time, f of the root must be equal to 0, but f of -1 is not equal to 0, so -1 is not the root. Let's move on to the right hand side and let's go ahead and examine the middle point. The middle point over here is 1, so like I said, the middle point between 0 and 2 is x equal to 1. Now f of 1 equal to 0, because right here we have f of 1 equal to 0. So this proves that x equal to 1 is the root, which is also known as the solution for the function f of x equal to x minus 1. Let's go ahead and take a look at another example. Our last example is as follows. Use the intermediate value theorem to prove that the equation square root of 2x plus 5 equals to 4 minus x squared has a solution. To do so, let's first assume that f of x equals to square root of 2x plus 5 minus 4 plus x squared. We also have to assume that f of x is continuous in the interval from -2, including -2, to plus infinity. And this requirement is because we don't want to have a negative value for the root. The root will always have positive values or 0 value. So -2 will ensure that we're not going to have a negative value under the root. Now let us zoom in to the interval -2, 4, where -2 is included. Now we will go ahead and evaluate f of -2, the endpoint. F of -2, if we do the math, it's going to be equal to 1. Also, we're going to evaluate another point, and for this case we will evaluate f of -0.5. And if we do the math, f of -0.5 will end up being equal to -1.75. Now that we have two values, f of -2 and f of -half, since f of -2 is equal to 1 and f of -half equal to -1.75, then f of -2 and f of -half, they have opposite signs. Since they have opposite signs, we can conclude that the function has a solution in the interval -2, -0.5, including both, including -2 and -0.5. That's it for now, and thank you for watching and have a nice day.